Welcome to Day 0 of KubeCon North America 2020. My name is Erin Boyd, and I will be talking today about how embracing cloud-native methodologies has changed the conversation with customers and developers when we talk about storage in particular. I was excited to be asked to present this keynote this year for Cloud Native Data Management Day, which used to be called Cloud Native Storage Day. I think having an emphasis on the data has been an evolution in our journey to incorporate how we have viewed storage in terms of legacy deployments in the past and how we create and utilize it more in a cloud-native fashion in the future. It is also really how I got started in my journey around storage. I joked to colleagues that I'm not really a storage engineer, I just play one on TV. But the more the ecosystem continues to evolve and grow into what we think of as cloud-native storage, I fully embrace that title. I've always been driven by what data means and how we can use it. From my time in college to working on 3D models to Fusion to working in big data and analytics. The key to all of these is how we can store, use, and most importantly, trust our storage technologies to persist our data and keep it secure. Today, I hope to help you better understand how we make architectural decisions in the past and in the cloud-native world, and how when structuring our applications and workflows, we should consider how our framework and our requirements affect these decisions. Lastly, I want to give a brief update about what we are doing in Kubernetes community to fill some of these gaps and to make the cloud-native storage story more complete. First, I want to set a baseline on what we define cloud-native to be. This definition, provided by the Cloud Native Storage Computing Foundation, also known as the CNCF, took months to finalize, and I think it does an excellent job articulating what it means to be cloud native. I have bolded the words I really think capture and drive our purpose in this community. Cloud native technologies empower organizations to build and run scalable applications in modern dynamic environments such as public, private, and hybrid clouds. Containers, service meshes, microservices, immutable infrastructure, and declarative APIs exemplify this approach. These techniques enable loosely coupled systems that are resilient, manageable, and observable. Combined with robust automation, they allow engineers to make high-impact changes frequently and predictably with minimal toil. To empower, to give customers more freedom to innovate at scale. Dynamic. Our ecosystem is constantly and organically unfolding through our open source model by incorporating diverse use cases and perspectives. Declarative. The formalization of APIs in Kubernetes is one of the foundational pillars to its success, and a model is vital to its ability to abstract out things, like storage. Resilient, manageable, observable. I think we all can agree that having the ability in a distributed, complex system to know how to understand the flow and use of our data to be persisted reliably is of paramount importance. Minimal toil. I love this one. It accepts that we are going to move fast and with great impact, but we are going to try to do it in a way that reduces headaches, and that is great for everyone. It also lets us admit the system isn't perfect, but we are moving forward in the same direction by embracing this philosophy. Let's consider how we approach requirements. There is no one-size-fits-all. The way we might install a database within a cloud-native environment can leverage many different persistent patterns. Applications also have different requirements around logging, backup, DR, as well as placement and distribution. With Kubernetes being created on the idea that all applications are stateless, we fully recognize that even for short-lived processes, we are creating stateful artifacts from these workloads. Next, when we are discussing requirements with our users, we must recognize that the application owners and our developers are all at different stages of maturity in their move to the cloud-native model. Some customers are just wanting to port their legacy apps as VMs running in containers, while others are fully embracing this model to containerize and tune their workloads for the cloud. Also, there are various patterns of topology, and depending on the needs of both customers in terms of performance and latency, storage decisions cannot be made without understanding the overall view of how it is to be deployed and accessed. Lastly, storage concepts presented in Kube as storage have varying degrees of persistence, and it's important we understand when and how we leverage these different models. Let's start by looking at our typical legacy application. Traditionally, these were monolithic, specifically created and tuned for one use case. If running on-prem, admins were able to control what hardware is used and how big of a pipe we needed for a network. Many times, upgrades required downtime and were very difficult to scale up and back down dynamically. Also, multi-tenancy is harder and is not managed across many systems as a coherent solution across a wide variety of applications and well-defined to a unified security model. The behavior of the application might be tightly coupled to having specific disks for throughput and IOPS, as well as network bandwidth. Lastly, and I think this is the most important differentiator that Cloud Native offers over the legacy application model, is that it requires a physical person to install and configure storage on behalf of the application owner. A good example of a monolithic application might be one that has dependencies around reading and writing to a database that is time-boxed around when it needs to complete this process. Perhaps it's running big data and analytics as part of its workload. Storage is handpicked and managed by an administrator, and the network is guaranteed. So as we look to migrate this to cloud-native architecture, let's take this example and apply it to the storage attributes we consider when making this move and how they are different between the two models. This list was created as part of the CNCF Storage SIG white paper to help users create metrics and build understanding around storage concepts. I highly recommend it as a guide to formulating your cloud-native requirements and understanding how we have measured these attributes in the past as part of our legacy application. Let's start with durability. I like to think of durability in terms of redundancy. How many copies am I maintaining? Am I creating a single point of failure for my application by only maintaining a single copy, or maintaining all the copies within the same data center or availability zone? Being able to measure how durable the data is in this system gives the user confidence it's safe and secure. Since storage vendors traditionally built this into their storage system and disk technologies, when we move to a cloud-native architecture, maybe even across clouds, we can no longer rely on specific technologies to guarantee this durability. Thus, we have to use other means to provide that durability, such as scaling the application and the storage out across availability zones or across clouds, and leveraging the capabilities of the applications themselves to self-replicate and manage the data as part of its native functionality. Consistency. Traditionally, this metric is measured by RPO, or recovery point objective, meaning that in the event of a failure, how much can we tolerate losing a certain amount of data before it has real business impact? Many times, to gain more performance, users will favor soft or eventual consistency with the idea the system will catch up at some point and the data will be reliable, but not immediately. In a cloud-native topology, a user may not have disk choices or even network that can accommodate strong consistency, and therefore we measure instead the availability of the application and the data it relies on to function. Since the two in the cloud-native world are not tightly coupled, it's often a challenge to know what the state of things are and to synchronize the application. Performance. This is often a contended metric, even in legacy applications where we have well-established benchmarks and are able to control all aspects of the measurement. The CNCF Storage SIG has recently published a white paper to help users decipher how we can accurately judge this in a cloud-native way. The reason being it's so hard to understand and control are all the variables within the system, and that with one or two factors can throw the metric off completely. However, this list on the right is a good view of what we should be considering in a cloud-native architecture. Things like latency, throughput, and measuring completed storage operations over a set interval are good ways in determining how performant a storage solution might be. Many cloud providers also publish IOPS for each level of service they provide as well to help gauge in making that decision when running on the cloud. Scalability, I think, is one facet of cloud native that we can really harness over what is more quickly possible offered within the legacy environment. Though several storage vendors have outstanding metrics on scaling to very large numbers, the time to enable this is limited by disks on hand and the availability to install, configure, and make the storage readily available. Whereas the dynamic nature of cloud-native systems really shine with being able to request and get storage within seconds. Scalability is also something that is easily measured and compared between both of these models. Availability. In traditional storage systems, we use recovery time objectives, or RTO, similar to RPO with consistency, to understand the availability of the system after a failure in regards to its uptime. In a cloud-native environment, we aren't typically measuring just the availability of the disk, as we would in storage, but rather the application. Also, depending on how applications are scheduled in a cluster, it could vary depending on the priority and scheduling of these different applications. The last storage attribute is a key differentiator for being able to improve the velocity of your development and persistent usage. Traditionally, the storage layer and control was specifically administered via a storage admin and through an interface very separate from the application admin. The structure of Cloud Native to abstract out the common functions through the API allows users to leverage, provision, and use the storage with little knowledge to the storage technology underneath. So though it may seem there are more benefits on the surface to how we traditionally use storage, I think when we consider the problems we are trying to solve today in terms of scale and innovation, we consider these reasons to move to Cloud Native. The speed of development is improved as users can focus on their application rather than all the factors of the infrastructure. Through separation of concerns, components can be managed and update without other impact to the systems. With the ability to use intelligent scheduling models to land applications across many different systems, a higher throughput and utilization can be obtained through a cloud-native model. By abstracting out the storage infrastructure, we present the common pieces needed for storage and allow the user to use what they need and when they need it more dynamically. Data agility, which was on the front of many of our minds during the discussions I had with several contributors at KubeCon Barcelona. We recognize that operating in a hybrid cloud forces this function and provides value in a way that only cloud native can. So now that we have reviewed how to change the requirements we are gathering around storage from legacy to cloud native, let's look how we would take our sample legacy application and convert it to Kubernetes. First, we would want to break it out into all its microprocesses. With this, we would then want to consider what are the needs of the application in terms of storage types. Is this a highly performant application that needs block or even local storage? Or am I sharing this storage with others and I need a more file system interface? Next, I consider what types and levels of storage are available to me via my storage class. Can what is available within the namespace serve what I am trying to accomplish? Keep in mind that Kubernetes doesn't have the same ACLs as we understand them from a storage file system perspective. Take time to understand the limitations of the network, as it will directly inform the performance of your storage capability. Note, Kubernetes doesn't provide a native means to back up, recover, or quiesce applications with the storage layer, so these are often handled by the vendor solutions themselves. Part of abstracting the storage layer out is understanding how we use and provision storage in Kube. Years ago, the Container Storage Interface, or CSI, was created as a standard to attach to the infrastructure in a way that was more flexible for our vendors. It allows the ecosystem to grow faster and provide better quality and functions much sooner. This change, though, also pushed some of the standard functionality you expect from the storage layer to be pushed to the edges and can make it difficult to have a cohesive story for things like backup and DR, as well as data policy and governance, at least today. The data is key. From capturing, storing, to using and securing our data, storage is the foundational pillar our data is built on, and we are collectively driving these values within the community to make sure it meets the ever-changing demands of our fast-paced cloud world. I'm proud to be part of this community and excited to continue to see how we shape and deliver in this space. I can't wait to hear your questions and see how you feel like we should reshape requirements moving forward in a cloud native fashion.